In this video, I'm going to walk through the Chapter 4 quiz so you have an idea of what answers were expected of you. So for number 1, we are mixing two solutions and we have to write the balanced overall molecular equation, the complete ionic, and the net ionic equations for this reaction. The first thing that we need to do is to figure out what is going to form. So it tells us that a precipitate of iron oxide hydroxide is going to form. So we know that we're going to get iron 3 hydroxide here. OH has a -1 charge. Iron 3 means that it's iron plus 3. And then we are also it's going to be a double displacement reaction. So we are going to get potassium nitrate, KNO3. We need to make sure that we balance this equation. And we can see that we have 3 NO3s, so we're going to need a 3 out here. We have 3 OHs, so we're going to need a 3 here, and that should balance it out. Our complete ionic equation is going to be, we have to make sure that we bring these coefficients down, so 3K plus 3OH minus plus Fe3 plus 3 NO3 minuses is going to produce Fe3 plus. Oops, sorry. I forgot my phases here. So this is a solid and this is an aqueous. And so this actually is going to stay as a solid. We have FeOH3 plus 3K plus 3 NO3 minuses. The net ionic equation is anything except for the spectator ions. So we get rid of these spectator ions, and we see that we get 3 OH minus plus Fe3 plus is going to produce FeOH3 solid. Okay, and these are aqueous. A couple of mistakes that I saw were not carrying down this coefficient up here. Making sure that you are actually balancing the equation. So make sure you balance the equation. Also, there were some issues with being able to write out the formulas based off of the charges of the ions. So make sure that you can do that. That's something that we covered in the first unit. Okay, number 2, what is the oxidation number of sulfur in each species below? So we know that fluoride is an halogen, and so it's going to be -1. There are 6 of them, so we get -6 total, which means sulfur is going to be a +6 oxidation number. If we look at sulfurous acid, we know that oxygen is going to be -2. There are 3 of them, so we get -6 from oxygen. Hydrogen is bound to nonmetals, and so it is going to be a positive charge. So we have a +1 for hydrogen. But there are 2 of them, so that's +2. So in order for us to get a 0 net charge on this, we know that sulfur now must be +4. Let's look at number 4. We apparently skipped number 3 here. So we're going to identify the species being oxidized and what is being reduced in each of the following reactions. So we need to be able to figure out what the half reactions are and whether they are gaining or losing electrons. So Cr plus is going to Cr3 plus. It's becoming more positive. It's going from +1 to +3, which means that it must be losing electrons, loss of electrons. Remember, we have oil rig. Oxidation is loss, and so this must be oxidation. And then on the other side, we have tin 4 plus that is going to tin 2 plus. It's becoming more negative, so it is gaining electrons. And so reduction is a gain of electrons, so that's being reduced. Down here, we have AS going to AsCl3. So AS is going to be 0, and over here you're going to have a +3. So 0 to a +3. It's becoming more positive, so that's going to be an oxidation. And you have chlorine 2, which is 0, going to a -1, which is going to be a reduction. You're going to be gaining electrons because it's becoming more negative. Okay, so let's look at number 5. How many grams of silver chloride will be produced if you mix these two different solutions together? So the first thing we need to do is we need to write out the equation. So sodium chloride plus silver nitrate is going to produce silver chloride plus sodium nitrate. That's our overall balanced reaction. It is balanced here. And so it says, okay, well, if we have this much of this reaction and this much of that reaction, that should send off signals that you are going to have to find the limiting reactant. And to do that, since we are solving for grams of AgClS, we are going to be, I want to just go ahead and find the mass of that there and see which one is smaller. Okay, so I'm going to say, okay, well, for sodium chloride, I have 0.2 liters. And I know that I have a 1.3 molarity. Now, molarity equals moles per liter. That's our conversion factor here. Okay, so I have 1.3 moles in 1 liter of NaCl. Okay, my molar ratio here of NaCl to AgCl is a 1-to-1 molar ratio. So I get 1 mole of silver chloride for every 1 mole of sodium chloride. And I will then look for the molar mass of silver chloride. And the molar mass of silver chloride, looking at the periodic table, 143.321 grams. If I do that, I get 37.26 grams of AgCl. So now let's look at what if I used up all of my silver nitrate. Well, my silver nitrate, I have 0.3 liters, and my molarity here is 0.6 moles in 1 liter of AgNO3. And it's a 1-to-1 molar ratio, AgCl to AgNO3, looking at the balanced equation. And I can convert that into grams as well of AgCl. And if I do that, I find that that is 25.798 grams of AgCl. So AgNO3 is the limiting reactant. It will only make 25 grams of AgCl. Now we need to look at significant figures, and you can see that we have 1 sig fig here, and so we need 1 sig fig here, which will give us 30 grams of AgCl. All right, so now we are looking at a redox reaction where we're looking at an acidic solution of this reaction happening below. So the first thing we want to do is write our half reactions. So we have SO2 is going to go to SO4 2 minus, and we have Cr2O7 2 minus going to Cr3 plus. All right, so what we are going to do is balance out our anything that's not hydrogen or oxygen. Okay, and I'm going to do 1/2 reaction at a time. So this first half reaction, we are going to balance out anything. So the sulfurs, there's the same number of sulfurs, there's just different numbers of oxygens. Now we're not going to change the number of oxygens by like adding a coefficient out front, because then that changes the number of sulfurs and they all come together and it would never ever balance. It would never work. So the only way to get oxygens to balance is to add water into the equation. Now water is already there because it's an aqueous solution. So we have 2 oxygens here and 4 oxygens here, which means we need 2 more oxygens. So we're going to add 2 waters to get our 2 oxygens. So now our oxygens and our sulfurs are balanced, but we've added in some hydrogen. How many hydrogen? 4. So we're going to have to add 4 hydrogen to the other side of the equation in order to balance out those hydrogens. Now the hydrogens come in the form of H pluses because we are in acidic solution. So we get these H pluses that are floating around in the acidic solution that we are working in. So they're available to participate in this reaction. All right, so now we have everything balanced except for the charges. Over on this side, we have a charge of 0. Over on this side, we have a charge of -2 and +4, so that's +2. So to get the two sides to equal, I can add 2 electrons over here to get us to 0. So both sides are at 0. All right, so that's that half reaction. Let's go do the other one. So we have chromium oxide, and then we have chromium over here. And so we're looking here at this chromate ion. It has 2 chromiums, and we just have 1 on the product side, so I'm going to add a 2 out front here. So now my chromiums are balanced. Now I'm going to balance my oxygens. To do that, I'm going to have to add water. How many water? Well, then we need 7 oxygens, so 7 waters. That gives us 14 hydrogens, so I'm going to add 14 hydrogens on the other side. And then I have to balance the charges. So what's the charge up here? We have 14 plus and 2 minus, so that's 12 positive. And on this side we have 6 plus, so 6 positive. So that means that in order to balance them, I'm going to have to add 6 electrons over on this side of the equation. All right, so now that is balanced out, what are we going to do? We have to add these 2 half reactions back together, but we have to have the same number of electrons that are being lost as they are being gained. And we don't have that right now, so what we're going to have to do is we're going to have to multiply everything up here by 3. So we are going to get 6H2O plus 3SO2 is going to produce 3SO4 2 minus plus 12 hydrogens plus 6 electrons. And now we can add it all together because number of electrons is balanced. So when we add this all together, we are going to get 6 electrons plus 6H2O plus 14 H pluses plus 3SO4 plus chromate is going to produce 3SO4 2 minus plus 2 Cr3 pluses plus 7 waters plus 12 hydrogens plus 6 electrons. Okay, I can go back to my black here. The 6 electrons are going to cancel each other out. We have hydrogens on both sides. They're going to cancel each other out as much as possible. We have waters on both sides. We're going to cancel those out as much as possible, just like variables in an algebraic equation. So these will cancel out. We should get 2 hydrogens plus 3SO4 plus chromate. Going to produce 3SO4 2 minus plus 2 Cr3 pluses plus H2O. And that is your final answer. All right. The final question is about the activity series and whether this reaction will occur. So it's asking, is zinc more reactive or is potassium more reactive? And if you look on the sheet, potassium